Now in today's lesson, we are going to discuss the infamous kernel trick. Now if I had to condense the main idea behind kernels in one phrase, I would say that kernels replace feature maps. And what do I mean with this? So last lecture we've seen that we can apply nonlinear feature maps to our observations and still do linear regression on them, on those feature mapped observations. But we've also seen that there may be a lot of computational overhead when applying a feature map phi to our observations. In particular, we have seen that the normal equation, so the solution to our linear regression problem, where we find the optimal parameter vector W star, involves the inversion of a k by k matrix, which scales quadratically in the numbers of features we include in our linear regression. Now the kernel trick is a way to completely avoid the explicit evaluation of a feature mapped observation. Now in this lecture I will show you that using the kernel trick you can completely remove this object, the feature mapped dataset X, from the calculation of the loss function, the solution to our regression problem, and the production of a prediction vector y hat. We will do so by finding equivalent formulations of these functions, the loss, the solution, and the prediction function, and these equivalent formulations will involve what's called Gram matrices. And Gram matrices are essentially outer products of identical matrices. So we have phi x times phi x transposed. Now to see that Gram matrices are indeed really useful for what we are about to do, we first have to observe that this particular Gram matrix, phi x times phi x transpose, is of the following form. So it's the n by n matrix containing inner products or scalar products of the feature mapped observations. So this first row of this Gram matrix contains all possible inner products involving the first feature mapped observation as the first argument. So we have the inner product between phi x1 and phi x1. Then we have the inner product between phi x1 and phi x2, and so on, until we reach the final entry, which is the inner product between phi x1 and phi xn. And we do this for all rows. Thus, the final row of this Gram matrix contains all possible inner products, where the first argument is the final feature mapped observation. And again, this object is of dimensionality n by n. Now in the next lecture we will discuss scalar or inner products more formally when we talk about Hilbert spaces. But for now, let's just consider them as a measure of how similar two points or two vectors are. And the reason why we think of the scalar product as a measure of how similar two points are is that if you take any two vectors and you normalize them, so you divide these vectors by their corresponding magnitude, then you will find that the scalar product between these vectors will also be normalized. So the scalar product between these two normalized vectors ranges from -1 to 1. And they can only produce a 1 if they are equal, and these two vectors will produce an inner product of -1 if they are the same but pointing in opposite directions. And if there are orthogonal to another, so if they have this 90-degree relationship, then the inner product will be 0. So again, this is why we think of the scalar product as a similarity measure between 2 points or 2 vectors. And now we follow this intuition and realize that this Gram matrix above contains the similarities between our feature mapped observations. So each entry corresponds to the evaluated measure of how similar two observations are in the feature space induced by our feature map phi. The final observation I want you to make for this Gram matrix is that the Gram matrix phi x times phi x transposed is symmetric and positive semi-definite. So let me prove this actually. So first let's recall that the entry at position ij of this Gram matrix happens to be the inner product between the feature mapped observation xi and the feature mapped observation xj. And the symmetry of this object is actually quite obvious because it's a direct consequence of the inner product being symmetric. So in the next lecture we will see that one of the requirements for an inner product is that this mapping is symmetric, but we can exploit this fact, this axiom right now already and see that for every integer combination ij, we have that the inner product between feature mapped observation xi and the feature mapped observation xj is equal to the inner product between the feature mapped observation xj and the feature mapped observation xi. So switching the order of the arguments doesn't matter for the evaluation of the inner product. And as a direct consequence, we have that the entry at the position ij of this Gram matrix is the same as the entry in the position ji. So for this positive semi-definiteness property of this Gram matrix, we evaluate this expression for every vector v in Rn. So v transpose times this Gram matrix times v. So recall from last lecture where I talked about positive definiteness in the context of convexity, that this produces a scalar. So looking at this sharply, you will realize that this is a double sum over indices. So this is actually equal to the sum over all index combinations ij of vi, the ith component of this vector v, times the entry at the position ij of this Gram matrix times the jth entry of this vector v. This is essentially the definition of this vector matrix vector multiplication. And then we recall that this entry corresponds to the inner product between these two feature mapped observations. And then we can employ the linearity of the scalar product. And what this allows us is to push the vector entries vi into the first argument of this inner product. So we now sum over all indices I. And for each term of the summation, we multiply the ith entry of the vector v, multiply it with the feature mapped observation xi, and this now becomes a constant essentially. It will be fixed for all summations over j. And for this equality, we can employ the linearity again and do the same for the summation over j for the second argument of the inner product. So we end up with this inner product where the two arguments are summations over all vector entries v. So now we observe that these two entries are in fact identical now. And we call these entries now y. And y is some vector in Rn. And finally, we observe that the inner product between two vectors y is equal to the squared L2 norm of that vector y. From last lecture, we know that the norm of any vector is positive or 0. And we have this final inequality. So note that this potential equality to 0 implies that we have semi-definiteness. So if this final object of this vector matrix vector multiplication is not strictly positive, but only larger or equal than 0, then we have positive semi-definiteness. But nonetheless, we have shown that this vector matrix vector multiplication yields a scalar that is larger or equal than 0, and therefore we have shown that this Gram matrix is indeed positive semi-definite. Now we come to the central statement of this lecture, which is Mercer's theorem. And note that first we will only look at a simplified version of Mercer's theorem. In a later lecture, I will give you the full version of Mercer's theorem, but for now, let's consider the simplified version. So this theorem states that a symmetric function k, and symmetric means that the order of the arguments doesn't matter, can be expressed as a scalar product. So k of xi and xj is equal to some inner product of two feature mapped observations xi and xj for some phi, if and only if the kernel matrix k, which is a matrix with dimensionality n by n, which contains as its entries these evaluations of the kernel function, is positive semi-definite for any possible collection xn. So again, for any collection of observations we may have available, we will construct these evaluations of the kernel function, and these will then be the entries of our kernel matrix k. And if for any collection xn, this kernel matrix turns out to be positive semi-definite, then we have that these kernel entries are equal to some inner product of some feature mapped observations. And this is actually the kernel trick. So we have this kernel matrix k, and as its entries, it contains these evaluations of the kernel function for all our observations. And if that thing is positive semi-definite, we have that it equals this object, a matrix containing the inner products of feature mapped observations for some phi. And hopefully you will recognize this object as the Gram matrix we were talking about a few minutes ago. Now the kernel trick lies in the fact that this bivariate function k provides an equivalent expression to the inner product of two feature mapped observations for some phi, and it may be that the evaluation of k is much cheaper or even possible as compared to the inner product of two feature mapped observations. And why do I say possible? It may be that your feature map phi maps the observations you have available to an infinite dimensional space. So essentially you have infinitely many features to model your data with. And this sounds great, right? You would like to use that. But calculating the inner product of infinite dimensional objects is not feasible for finite machines as our computers. So in that case, it's not possible to calculate this inner product. But there are kernel functions that were shown to be equivalent to the inner products of two feature mapped observations where the feature map maps into an infinite dimensional space. And we can evaluate these kernel functions k, but not this explicit inner product. And again, this is the kernel trick. Please let that sink in. Observe that Mercer's theorem gave us equality between the kernel function and the inner product of some feature mapped observations. Now with this equality, we have two possible situations we might be facing. So in this first scenario, which arguably is less interesting, we start with a feature map phi we want to apply to our data, to our observations. And in this scenario, we write down the scalar product of two feature mapped observations xi and xj explicitly. And it might happen that the scalar product of these two feature mapped observations simplifies nicely. And in that situation, we define k to be the simplified expression. In the second scenario, we start with a bivariate function k, which satisfies the properties that are required by Mercer's theorem. Namely, k is symmetric, and k, the kernel matrix that is induced by k, is positive semi-definite for any collection of observations you have. And by Mercer's theorem, we then have that the evaluation of k for any two observations is equal to the scalar product of two feature mapped observations for some phi, and this phi may be intractable but interesting for our problem statement. So the second scenario is much more interesting than the first one, because in the first scenario, all you can do is really just use some algebra to cancel a few terms in most cases. But for the second scenario, you can show via Mercer's theorem that some kernel functions map into really interesting feature spaces that otherwise wouldn't be tractable computationally, or even possible in the case of infinite dimensional feature spaces. And again, the kernel trick is that you only have to evaluate this possibly much simpler function k instead of the inner product of two feature mapped observations. So to really hammer down this idea of the kernel trick, let me draw an illustration. So we have this input space, this data space calligraphic x, in which our observations live. So here's x1, here's x2, and we have this feature map phi that maps these points in calligraphic x to some higher dimensional space. And in the next lecture, we will see that this is a Hilbert space. You don't need to know what a Hilbert space is just now, but this is the set of feature mapped observations where each observation comes from the input space. And we apply this mapping deliberately because we want to work with nonlinear combinations of our original features in order to use a linear model to model nonlinear phenomena. That's the idea. And in order to run our linear regression, we have to evaluate the scalar products of feature mapped observations. And this operation yields a scalar, hence the name scalar product. Now the kernel trick is actually skipping this intermediate step of mapping into this higher dimensional space explicitly. We just go straight to the evaluation of that value that we need, the scalar. And using the kernel trick, we never have to explicitly evaluate these feature mapped observations to arrive at the scalar that we need, since the evaluation of the kernel function is equal to the inner product of two feature mapped observations. So I think it's time to have a concrete example. So consider this mapping phi that takes as input a two-dimensional observation with the components xi1 and xi2, and phi maps this vector to this three-dimensional vector where the first entry is xi1 squared. Second entry is the product of these two original features times the square root of 2. And the third entry is the square of the second entry, xi2. So we have this feature map phi, and we want to arrive at the corresponding kernel function. Again, this is the less interesting case where we start with the mapping phi and arrive at the kernel function. On the next slide, we will look at the case where you start with a kernel function and arrive at the corresponding feature map. But let's still do this little exercise. So we want to evaluate the inner product of two feature mapped observations. So this observation is xi and this observation is xj. And just writing out this inner product explicitly using the definition we have above, we arrive at this summation. So this first term in the summation is the product between the first entry of our feature mapped observation xi and the first entry of our feature mapped observation xj. For the second term in the summation, we have the product of the second entry of our feature mapped observation of x and the second entry of the feature mapped observation xj. And I just noticed that there's a 2 missing because we have the square root of 2 for both feature mapped observations, and square root of 2 times the square root of 2 is 2. So here's the 2. And all the other values in this product are the corresponding values in the second entry of the feature map for xi and xj. And finally, the third term of this summation is the third entry of our feature mapped observation xi times the third entry of our feature mapped observation xj. And using one of the binomial formulas, we see that we can simplify this expression as such. So we have the sum of products of individual entries of the two vectors xi and xj. So here's the first entry of xi times the first entry of xj, plus the second entry of xi times the second entry of xj. And then we take the square of that sum of products. And we observe that this is equal to the square of the inner product of the untransformed observations. So here, these are the plain observations, no feature map applied. We just take the square of the inner product of those two. And we define this to be our kernel function, taking as input the observation xi and xj. And note that the critical part, the kernel trick in this situation, is that we simplify this expression to this one, where we have fewer individual computations to execute than for this expression. So evaluating k, which essentially is this bit here, is cheaper than first applying the feature map and then calculating the inner product between the two feature mapped observations, which is this expression. But let's turn our attention to the more interesting case where we have a function k that satisfies the requirements of Mercer's theorem. And finding such a k is actually quite difficult. But there are some functions that were shown to be valid kernel functions, and some examples are the polynomial kernel, the Gaussian kernel, and the Laplacian kernel. There are, of course, many more kernels, so if you want more examples, then have a look at this blog post where someone compiled this long list of valid kernel functions. But let's have a look at these 3 examples in particular. So the first one is the polynomial kernel, and this polynomial kernel is of the following shape. So in it, you have the inner product of untransformed, of unfeature mapped observations u and v. You might add a constant, which is a scalar, a real number, and you take that expression to the mth power, where m is a natural number. And you can go back to the previous slide and you will see that the kernel that we derived is a special case of this polynomial kernel where gamma is equal to 0 because we don't add a constant to the inner product of our untransformed, unfeature mapped observations, and m was equal to 2. Go ahead and have a look at the previous slide and verify that this is indeed the kernel that we found for this arguably degenerate case. It should be noted that the polynomial kernel, although it's nice as an illustration to demonstrate the principle behind the kernel trick, it's not used in practice all that much. So this is actually a not so popular kernel in practice. A kernel that is often used in practice is the so-called Gaussian kernel. Sometimes it's also called the RBF kernel. What we compute is the exponential of some negative number, And this negative number is the squared norm of the difference between our observations u and v, divided by 2 times some variance sigma squared, where sigma is some positive number. It's a scale parameter, essentially. And recall our intuition behind the kernel functions, which are equal to the inner product of some feature mapped observations. So the similarity of 2 observations in some feature space is also a similarity measure, essentially. This is largest if the squared norm of the difference between these 2 vectors is small. So if they are close to another, essentially. And this will decay for the case where u and v are vastly different vectors, because then the squared norm of the difference between these 2 vectors will be large. And then you have this large negative number as the argument of your exponential. And this will decay rather quickly then. And on the next slide, I will show that this Gaussian kernel maps into an infinite dimensional feature space. So this is going to be exciting. And this last example is the Laplacian kernel. And this looks quite like the Gaussian kernel, but we don't take the square of the magnitude of the difference between the 2 observations, and we don't square the sigma. So this is just a plain scale parameter, essentially. I will now show that the Gaussian kernel maps into an infinite dimensional feature space. For this, we actually also need the polynomial kernel. You will see in a minute why that is. So let's recall the definition of the polynomial kernel. It's k of u and v equals the inner product of u and v plus some constant gamma to the power of m. And also recall this Gaussian kernel where k of u and v is equal to the exponential of some negative quantity, and this quantity is the squared norm of the difference between these 2 vectors divided by 2 sigma squared. And for this proof, without loss of generality, we will assume that sigma is equal to 1. So if sigma is equal to 1, we have that the Gaussian kernel equals this expression, so the exponential of -1/2 times the squared magnitude of the difference between u and v. And we have seen several times now that we can rewrite this squared norm of 2 vectors as such. So it's the product of u minus v transpose times u minus v. And if we then transpose these individual vectors inside bracket, we have this expression. So you have to be careful. You have to also consider this negative v. So it's -1/2 times minus v transpose plus u transpose. And then we multiply this with u minus v. If we multiply out all of these expressions, we are left with these terms. And let's recognize that all of these terms are inner products. So we have the negative inner product of u and v, as well as here. So we have -2 times the inner product of u and v. And then we have the inner product of u with itself. So this is the squared norm of u. And then also the inner product of v with itself. This is equal to the squared norm of v. And I always seem to forget to close the brackets. And then if we multiply this -1/2 with each of these terms, then we have the inner product of uv -1/2 times the squared magnitude of u and -1/2 times the squared magnitude of v. And since the exponential decomposes into products, if the argument is a sum, we have that we arrive at this expression. So the exponential of the inner product of u and v times the exponential of -1/2 times the squared magnitude of u times the exponential of -1/2 times the squared magnitude of v. We call this constant cu, and we call this constant cv. And then we recall this famous identity that the exponential of some quantity x is equal to the infinite sum starting from k equals 0 to infinity of the terms x to the power of k divided by k factorial. So we can rewrite the exponential of the inner product of u and v as follows. It's the infinite sum starting from k equals 0 of terms inner product of uv to the power of k divided by k factorial. And then we multiply cu and cv to that expression. And since the inner product is linear, we can push in these terms cu and cv into the inner product, as well as the k factorial term. It also goes into the inner product. And we are left with this infinite sum starting from k equals 0 of the inner product of this weighted u vector and this weighted v vector to the power of k. And finally, we observe that this is an infinite sum of polynomial kernels of increasing dimensionality. So observe that each of these terms is a polynomial kernel where m is equal to k, and we increase the dimensionality towards infinity. And since we can rewrite this Gaussian kernel as an infinite sum of polynomial kernels of increasing dimensionality, we have shown that the Gaussian kernel maps into an infinite dimensional space. But let's return to our original goal of rewriting the loss, the solution, and the prediction function of ridge regression. And we will rewrite these functions in such a way that they only involve Gram matrices. And we can replace Gram matrices with our kernel matrices. And the kernel matrices are equivalent to the Gram matrices insofar as they have the same entries, but the entries of the kernel matrices are the evaluated kernel functions, and these are much more feasible computationally than the evaluated inner product of feature mapped observations as in the Gram matrices. So let's start with the solution of our ridge regression actually. And first we write down this solution to ridge regression again. So W star is equal to the inverse of phi x transpose phi x plus lambda times the identity matrix. And then we multiply this inverse with phi x transpose y. This was our solution to ridge regression. And we can reformulate this expression as such. So we essentially get this phi x transpose from this position all the way to the left. And also inside this inverse expression, we produce this Gram matrix. So at first sight, it's not obvious to see that this is indeed equivalent, but I will give you the proof on the next slide, of course. And we now see that we have this Gram matrix inside this inverse, and we can replace it with this kernel matrix K. And although we still have this phi x transpose on the left, which we cannot further simplify, we are done rewriting the solution to ridge regression, because we will see later that this part won't matter, because this will now be our parameter. And alpha, our parameter for kernelized ridge regression, is k plus lambda times the identity matrix, inverse of that times the true label vector. So again, this is the new parameter of our kernelized ridge regression, and we have gotten rid of the Gram matrix that we had in this expression. So as promised, I will now give you the proof that we can indeed rewrite this expression as this one. So let's start. So we want to verify whether this expression, so everything up to the y, is equal to this expression, which is everything, again, up to the y. Does the equality star hold? This is the question we are trying to answer. We first observe that the equality star is equivalent to this equality. So what we do is we multiply this expression, this phi x transpose phi x plus lambda times the identity, from the left to both sides. And since we have the inverse of that expression on the left-hand side, these will then cancel, and we are only left with phi x transposed. We multiply this expression from the left to the right-hand side. So for the next equivalence, we get rid of this inverse by multiplying this object to the right to both expressions. So we multiply phi x times phi x transpose plus lambda times the identity from the right to both sides. So for this left-hand side, we are left with phi x transpose times phi x transpose plus lambda times the identity. And for this right-hand side, we are left with phi x transpose times phi x plus lambda times the identity times phi of x transpose. And then we multiply out these expressions. And for this left-hand side, we are left with phi x transpose times phi x transpose plus phi x transpose times lambda times the identity. And for this right-hand side, we have phi x transpose times phi x transpose plus lambda times the identity times phi x transpose. And finally, we observe that these two expressions are equal, because phi x transpose times lambda the identity is equal to lambda times the identity times phi x transpose. So we have shown that this is equal. And since we have used a chain of equivalence relations, we arrive at the conclusion that the starting equality star is true. So we have shown that this expression is indeed equal to this one, and that the steps of the previous slides were justified. So now that we've seen that this is a valid reformulation of our ideal parameter vector W star, we can insert it into our loss. We are now rewriting the Ridge Regression loss. And recall that the loss is defined as follows. So we have the squared L2 norm. This is the squared L2 norm of our predictions minus the true label. And we have lambda times the squared L2 norm of our parameter vector W star. And if we now insert this reformulation of our parameter vector into every occurrence of W star, we arrive at this arguably quite messy expression, but we're going to tidy it up. So here we already have this Gram matrix, right? So this is good. And also for this second bracket, because they are identical. And for this expression, the squared L2 norm for our parameter vector, we have this one. So lambda times the transpose of phi x transpose times alpha. And then we multiply this with phi x transpose alpha. So for this next line, we just observe that this is equal to k, as well as this. And here we just apply the transpose to the individual factors of our product. And we then arrive at lambda times alpha transpose times phi x. And then we just multiply phi x transpose alpha to this. And here we also see that we have a kernel matrix. So we can rewrite this expression as follows. So we have k alpha minus y transpose k alpha minus y plus lambda times alpha transpose k alpha. And we see that this is the squared L2 norm of our predictions. Our predictions now look like this. So it's the kernel matrix times our parameter vector alpha minus y, the squared L2 norm of this. And then we have this. And this almost looks like the L2 norm of our parameter vector alpha. We just have this diffusion matrix K within the square of the parameter vector alpha. So this is our reformulation of the loss function. And observe that also for this function, we have gotten rid of all occurrences of phi x by exchanging the Gram matrices with the kernel matrices. So on the previous slide, we have seen that the vector k alpha seems to be our prediction vector y hat, because this is the vector we subtract the true labels from before finding the squared L2 norm of that. But let's verify that this indeed yields the prediction vector y hat. And for this, recall our solution to Ridge Regression. So this is W star again, and we generated an individual observation yi hat as follows. It's the inner product of the feature mapped ith observation and this parameter vector W star. And observe that this inner product is equal to this expression. So we have the feature mapped observation xi transpose, and then this parameter vector W star. And then finally, recall that we called this expression, this k plus lambda times the identity inverse of that times y. We called this alpha. And we are left with this rather compact expression, phi xi transpose phi x transpose alpha. This is an individual prediction, yi hat. And on the next slide, I will show you that you can simplify this expression to arrive at this one. So an individual prediction yi hat is equal to the sum over indices in our data set up to capital N, the number of observations we have available. And what we are summing up is the nth component of our parameter vector alpha times the kernel evaluated for observations xi and xn. So let's quickly verify that this is indeed true. And for this, we recall that the individual prediction is generated as the inner product between the feature mapped observation xi and phi x transpose times our parameter alpha. This is a real number. And the dimensionalities of all these involved quantities are as follows. So the feature mapped observation xi has dimensionality rk. The feature map dataset has dimensionality Rn times k, and our parameter vector alpha lives in Rn. And since our individual prediction is a real number, we can transpose it because the transpose of a real is equal to the real itself. And we are left with the fact that the individual prediction is equal to alpha transpose times phi of x times phi of xi. And now let's write out all of this explicitly. So we have alpha transposed, it's a row vector, times phi x, which contains the feature mapped observations as row entries, and this feature mapped observation xi, which is a column vector. And then first we do the multiplication of phi x and phi xi, and we see that this yields for each row the inner product between the feature mapped observation and the feature mapped observation xi. So this is what we have here. And since we can rewrite these inner products of feature mapped observations as evaluated kernel functions, we arrive at this expression. Now it's not hard to see that this is the inner product between the alpha vector and the kernel evaluations for the individual observations x1 and 2 xn as the first argument, and the fixed xi as the second argument. And this is equal to the sum that we have above. So the kernel function is per definition symmetric, so the order of the arguments doesn't matter. So we are done. So just to wrap up, let's rewrite the minimization problem of kernelized ridge regression. And we have that the loss is now not a function of our parameter vector w, but instead of our new parameter vector alpha. And this was the loss function we constructed for this case. This is our prediction vector y hat. And our ideal parameter vector alpha star is now the argmin of this loss. And this happens to be what we defined previously, because we already optimized w star and rewriting this entire business where alpha now is the parameter doesn't change our solution. This is the ideal parameter vector, and we have identified this before. And actually, this is it. We have completely kernelized ridge regression. We can calculate a loss. We can optimize, so we can find a solution to the minimization problem. And we can create a prediction vector y hat by multiplying the kernel matrix K with our ideal parameter vector alpha star. And again, this is the kernel trick. None of these calculations require us explicitly to evaluate any feature mapped observation. So anywhere where there are feature mapped observations, we have this kernel matrix instead, for which we have the evaluated kernel functions as entries, which are computationally cheaper to evaluate than the inner product of two feature mapped observations. And this is the kernel trick. Next time, we will dive into the more advanced concepts of this module, and we will start with the reproducing kernel Hilbert spaces.